Welcome everyone, I'm Chris Corde. I'm a Senior Director of Product Management with NSX Security. Basically, NSX, if you're not aware, is our network and security platform. Essentially, it's used in data center environments to perform microsegmentation from a security perspective and also security service orchestration. We also have a new product that we announced at VMworld a couple weeks ago called AppDefense, which its goal is to build upon the concepts of NSX. And to actually extend what we can do with network segmentation into the application layer and allow for least privilege of application behavior. So we'll talk a little bit about that today. So prior to coming to VMware, I've spent a number of years in the security industry, most notably at RSA. I was at RSA Security for probably 8 years. One of the interesting things that I had the pleasure, misfortune of going through during our time at RSA was a fairly major, significant breach of RSA infrastructure. So if any of you were aware or were RSA token users at the time, we in about 2011, were subject to a fairly sophisticated nation-state attack that stole the token seed records for the RSA two-factor authentication token. So there was about 70 million tokens that were currently shipped to customers at the time of the breach. Very similarly to what you're seeing with Equifax and the major breaches today, it was very difficult for us to know exactly which customers were affected by the breach, which token seeds explicitly were stolen. So we had to actually notify every customer that you potentially could have a breached token seed, token record, and that more or less had to replace every single one of those tokens. And some of them were software tokens, which were easy to reseed. A lot of them, if many of you are aware of, were hardware, physical hardware tokens that needed to be remanufactured and redistributed, which obviously caused a major, major disruption. So the interesting thing was we started looking at that time, because RSA very much at the time was an authentication and identity management company. That's what we did. We started looking at that time of, even though we were a fairly sophisticated security organization who had a lot of security capability and security talent, why is it that sort of we couldn't stay on top of a breach, right, and kind of get in front of it? And if we couldn't do it, given the fact that we had all these resources, how can we expect a lot of our customers to do it, especially as you started to see the growing trend of more advanced, more sophisticated attacks happening? So that's sort of led a lot of our early stage thinking and how we moved into more of a, I'll call it a security posture perspective and security management perspective. And there were a couple things that we found along the way. The first thing that we started looking at is we actually commissioned a study with McKinsey to go out and determine where people were spending the vast majority of their time, their budget, their effort from a security perspective. Clearly budget was going up. People were spending more and more dollars on security. So it wasn't a problem of just not throwing enough money at the problem. So we thought, well, it had to be a problem of where people were focusing their spend and their effort. So we looked at this, which is a fairly simplistic kill chain, right? If you're aware of the kill chain that's been published by MITRE, or there's one that's published by Lockheed Martin, this is a fairly simplified version of that. What we found was that an awful lot of security budgets and investment, this is time, this is people, this is money that you spend, products that you deploy, all go towards the upfront area of the kill chain, the infiltration portion of the kill chain. So that's about 70 to 80% of the budget we found was going towards stopping infiltration. And then people spent sort of some time in their effort on the back end, 20% going through the propagation, extraction, exfiltration portion of attacks. The challenge with that is, think of this as a very asymmetric battle when you're dealing at the front end of the attack chain. The reason for that is an attacker can try 1,000 times, 1,000,000 times. They only need to be right once in order for them to do their job. You have to be right 1,000 times, right? One infiltration essentially breaches this point, and if you don't have enough protection through the edge of the kill chain, through the middle portions of the kill chain, effectively the attacker starts to have free reign and starts to be able to do whatever they want. So if you're focused entirely on infiltration and saying, I'm going to create a wall and that wall is going to be impenetrable, you better be sure that it's an impenetrable wall. And that's just a very, very difficult problem. Considering the fact that most infiltration points are end user machines, considering the fact that most infiltration points are zero-day attacks and that these are new methods that attackers are coming up with, the notion that you can be able to stop things at the infiltration point is very, very difficult. So as you start to get further down into the kill chain, the odds sort of flip a little bit more into your favor. Like, think about this as an attacker, when they get past your front door in your house, they don't have a blueprint of exactly what your house looks like. They're sitting there with sort of in the dark, and they're trying to kind of poke their way around, trying to figure out where the valuable information is or where the valuable pieces of property are in your house that they're trying to get access to. And you should have a pretty good handle of where you keep your valuables, and you should have a pretty good handle on how you secure those things. And effectively, you start to have a little bit more of an advantage later on in the kill chain. So our thought process was, if you start putting more security focus deeper into the kill chain and actually have more layered security through the propagation and extraction portions of the attack, you can actually be in a much better place to stop major breaches from happening. A good example I like to give about this is like when you think about ransomware. Ransomware, for the most part, has built-in propagation mechanisms. The reason why it becomes so powerful is that it gets an infiltration point on one machine, and it can quickly propagate itself to a lot of machines. That's how you see things like ransomware taking down entire data center environments, right? Taking down entire hospitals and keeping them offline. It's because they propagate themselves very fast. That's their job. So if you can more or less say, look, maybe I can't stop the initial infiltration, but I can stop the propagation of that attack and limit it to a very small segment of the environment, you've effectively limited an awful lot of the damage that something like that can do. So focusing a little more on the inside is actually a fairly effective mechanism. It can stop a lot of significant breaches from happening. And think about this as there's differences between security events, which are things where someone might be inside of your network, and a major breach, which is someone has actually stolen and taken critical information. Right? There's people sitting inside the VMware network right now. I can guarantee it. The question is, are they breaching the network? Are they taking anything out that's valuable? If they're not, it's not really a security incident or a breach that you need to be concerned about. So you always need to make sure that you have this layered approach. Now, the reason why people don't like to spend a lot of time in the middle area of the attack chain, the propagation and extraction portions of the attack, is, again, another simplistic picture, but they kind of are left dealing with something like this, a picture that looks like this, which is they don't have a really good understanding of normal behavior, application behavior, what's expected, what's not expected. So when they think about looking at things that are happening, in their data center, they typically dump a lot of things into this large gray area in the middle, which is unknown. And they can classify a very small sliver of that behavior as known good. Like, this is a well-observed, known behavior. I understand that's the way the application should behave and everything's fine. They can classify some things as known bad. Like a typical approach is take some indicator of compromised feeds, take some, some known bad IP address feeds or known bad hash feeds, and say, layer that on top of some log data. And okay, I can filter out some known bad, stop a known signature from running. But the rest of it, like I said, is just dumped into this middle area, into this gray bucket. And again, we at RSA actually were one of the prime offenders in this model, right? And we had a product called NetWitness, so it was renamed Security Analytics. Its job was to basically collect full packet information in the data center and dump it into a repository for you to look at. And there's not a lot of things you can do once you have that data in the gray area. The default answer is write some rules, some correlation rules on it, and see if you can kind of find some interesting angles or interesting connection points. Like, what if someone does a failed authentication 20 times in a row? Or if you have a firewall rule that's been broken 20 times in a row. That's a rule-based correlation. That's saying, hey, I'm getting a bunch of logs and I'm seeing all this information, and I don't know who's trying to make that connection, but 20 times in a row is not good, right? So that fires an alert. The other thing you could do is just hire a bunch of good analysts. Get a bunch of good analysts in your security operations center, sit in front of a screen, and have them churn through all this data. Again, going back to the RSA case, this is exactly how we found our breach. Unfortunately, it was a little too late, but we found it by having a good analyst sitting in front of the screen, looking at log information and realizing that something was wrong. There was some information here that did not look like normal user application traffic behavior. And that's essentially how they triggered it. There was no other magic behind the scenes. But this just doesn't scale. I mean, this is good for the Lockheed Martins of the world. This is good for the NSA. This is good maybe for the major banks on Wall Street. And by good, I'm using the air quotes good, which is like they can at least try to do it. But it really doesn't scale to the vast majority of the market. So it's certainly not an effective model for an awful lot of organizations out there. And you're seeing some companies come up with interesting tricks around machine learning analytics that try to make sense out of this gray area. Again, this is a very nascent space, and it's also very prone to false positive. There was an interesting sort of article that was published by, I think, the ex-CISO of Google a couple days ago, where she was talking about how machine learning analytics, it's essentially good for stopping attacks that were born, in the 70s. It's not really good for things that are more recent, more sophisticated attacks, and they're too prone to false positives. So this is sort of the state of security. I mean, unfortunately, I don't think we've advanced, in most cases, very far beyond this, which is you're just dealing with an awful lot of unknown traffic behavior when you're looking at the inside of an attack chain. So most people just say, look, I'll focus on the front end. I'll try to prevent what I can. I'll prevent the 80% and sort of cross your fingers and hope for the best. One of the things that we often talk about as well is the reason why a lot of people are left dealing with gray area in the middle area of their attack chain. And why is that the case? Now, we often use this analogy of like a security professional when dealing with signals that are kind of just getting dumped to them on the back end about security events are essentially like doctors in a situation where if you brought your child to a doctor and you said nothing about symptoms or anything or what their normal behavior is or how they should behave or anything like that, and you just dumped them in front of a doctor and you said, here you go, tell me what's wrong, right? You're leaving the doctor essentially in a situation where they have to then look, using all of the potential known bad things that can possibly happen in the world, and try to find those inside the child, without any indication of what's good, what's bad, or what's normal, right? Which is an almost impossible task. It's not that the doctor doesn't know, about their job, that the fact that this is good or bad, indicators of health. It's the fact that without any indication of where to start looking, what's normal, it's impossible to do it, right? So they rely on this kind of relationship with parents, with people that know their children the best, to be kind of the first level of indication of what's good or what's bad behavior. And they need to be able to feed that information to the doctor to sort of provide some indicators about what's good or bad. And that starting point between the parent feeding information over to the doctor and the doctor being able to then layer on their expertise about maladies and sort of things that could potentially be wrong, creates this obviously a much more effective model of them being able to find and diagnose bad behavior. So the same is true sort of in the security world and in the infrastructure world, right? What you're dealing with here is, you cannot leave security people alone to just simply try to figure things out on their own. That's more or less the infiltration model. That's like, hey, I'm not going to know anything. I'm not going to have any a priori knowledge. I'm just going to try to run a model on top of the environment, create some rules, stop you at the front door, and that's as far as I can go. You need this kind of handoff. You need to be able to work more effectively with the infrastructure and the application owners who know their environment the best, right? They're the ones who are responsible for keeping infrastructure alive on a day-to-day basis. They're the ones who are responsible for making sure applications are running. They need to be able to feed information over to the security teams about normal, expected, good, intended state behavior so that the security teams can properly diagnose when things go wrong and when they see anomalies. And if you can do that, you can effectively shrink that gray area in the middle. You're now saying, look, I know exactly what known good behavior is, and I can effectively shrink the kind of things I have to do second guessing or reverse engineering on, and anomalies become a lot easier to spot and easier to see. So how do we do this? How do we embed more of this, this intended state knowledge, right? And this is sort of like, again, what could be the end results? If we knew more about the way applications should behave, the end results are you can move away from this current model, which is focused on malicious behavior, focused on trying to hunt down potential malicious indicators, which is, again, complex, it's noisy, it's difficult, it's kind of always sitting behind the 8-ball, right? Because attackers are constantly changing their techniques and the way in which they try to infiltrate environments. So you move away from that and you move more to a model where you're focused on validating the intended state behavior. You're saying, look, I know exactly the way an application should behave, and therefore I am going to continually watch and verify that the application is behaving the way I expect. And when you do that, the things that are actually anomalous instantly become clear. And it doesn't necessarily matter if that anomalous behavior is a new attack technique, if it's a brand new piece of ransomware, if it's something that has never been seen before in the wild, the point is it's different than what the application was expected to do. And when you have that, you know, all the fancy signatures in the world about malicious, known malicious pieces of software don't really need them anymore. You're focused then on saying things are acting differently than the way they were supposed to, and you can start locking them down, or you can get alerted very fast about when those things are deviating from normal. So this is the approach very much that we take with NSX on the network side, if any of you are aware of NSX. But one of the primary use cases, if not the primary use case of NSX, is around creating what we call a microsegmentation least privilege policy in the data center for network traffic, meaning that you know what's known, good, expected network behavior in your data center, and I can start to create segmented environments, walled off environments, where I can look at the way applications are behaving and then start to draw a line around the network segment to say that things should not be moving or deviating outside of that network segment and should not be acting abnormally based on that networking segment. So I don't have a ton of slides here on NSX, but again, I'll talk about it in the context of how we deliver this security model, both through NSX and what we're doing now with AppDefense. But the primary premise is the same, which is focus on application behavior, focus on understanding good intended state, and then effectively start enforcing that. And a firewall is not necessarily the most sophisticated security tool out there. What it is good is enforcing a known good access control list. So if you understand a good access control point of view, you can effectively start putting in proper segmentation rules across the board. And what we're doing with AppDefense is kind of layering that up another level and looking inside of the segments and seeing how the applications are behaving themselves. So one question we often get is sort of, well, why VMware? Like, what about VMware is actually well suited to solve this problem? I mean, before NSX, we weren't even a firewalling company. We weren't even a networking company. All of a sudden now we're solving not only networking issues for customers, but we're solving security issues for customers. And there's a couple of things that I think are interesting to point out about virtual infrastructure and the virtualization layer that make it unique, that allow VMware to actually solve this in a very interesting way. The first is the virtualization layer actually has a very good understanding of applications, the things that are running on top of the virtual infrastructure. And the reason for this is its core job, its primary job, forget about security, is to become a layer of abstraction between hardware and applications and logic and software running on top of it. And we do this both for compute, obviously, which is the core primary job of VMware, which is, say, take a piece of compute hardware, abstract it into a bunch of different logical compute instances. We also are doing it for networking. One of the primary, or the primary goal of NSX is to create a logical network where your networking decisions and your networking policies are governed in the software layer as opposed to being governed in the hardware itself. So in order to solve that problem alone, you have to have an understanding of what we call intended state. You have to understanding of what people are trying to do. I have to know what logical networks you're trying to create. I have to know how many machines you're trying to spin up. I have to know what utilization you expect those machines to have. I have to know what operating systems you're putting on those machines. I have to know, where you expect your routing, your switching, your firewalling policies to be. All that has to be in place, which is all intended state understanding of the workloads that are running on top of the virtual layer. We also have an interesting viewpoint to see runtime state. Every single system call has to be driven through the virtualization layer. Where the abstraction point between the operating system was making a system call, like open a file, connect to the network, start a process. Any of those things are system calls that have to hit the CPU, the hardware at some point. So they have to pass through the virtual layer first. So when you have that position to say, I'm proxying every single event that's happening on the machine, both from a compute perspective and a network perspective, I have a perfect viewpoint to see runtime state. I know exactly what that machine is doing, right? Without having to put anything else anywhere in the environment, I can see everything from the ESX hypervisor. So this ability to kind of cross what I expect to see from an intended state perspective and what I am seeing from a runtime perspective is a very, very important security signal, especially when you want more security to be driven around validating good intended state. So that's a very unique property that exists, right, in the virtual layer, right? It's this abstraction that allows us to place these interesting hooks for visibility. The other thing, which is actually one of the most unique things, is it's an isolated control point. If I was going to give one real good answer about why NSX has been so successful, and NSX is, a $1 billion product in market, right, at this point, probably one of the single most biggest security products out there. It's just one product, and it's delivering that level of value to customers. It's very simplistically our ability to use the virtualization layer, ESX, as an isolated control point, meaning you take something that used to live outside of the compute stack, like a firewall, and you take it and move it as close as you possibly can to the workload you're trying to protect, so that it has a lot of the context about that workload. It has all the information that's required to secure that workload, but it's still living in an isolated control point, meaning that if someone has compromised the virtual machine, they can't compromise your firewall. It's a different attack to compromise the firewall. That's a very, very important sort of model. People like security in depth. They like the notion that if you compromise one thing, you haven't compromised another thing. So the fact that we're able to live in this zone where we're so close to the workload that you can have policies written directly about one virtual machine, but we're still in an isolated spot, is a tremendously powerful capability. And we do this for NSX for firewalling. We do it also with AppDefense for more endpoint inspection and endpoint behavior validation. So we can actually see lower level events happening in the operating system, like a file creation or a process create or someone trying to communicate outbound or listen inbound. All those things can be inspected, seen, controlled from the hypervisor. So that ability to have this isolation point is extremely powerful. There's been a lot of research about it. I think it's only now we're getting to the point where, from a performance perspective, we're actually able to do this at scale. And that's really, with NSX, from a security point of view, its primary value is kind of taking the firewall and hugging it right close to the workload and being able to have firewalling policies driven around your specific applications and their behavior. And then the last piece is this interesting notion of automation, the ability to take action on a particular application or guest virtual machine as a result of some security policy or security event or security incident. And the reason why we can do this very easily is things are software defined. One of the more interesting aspects of any software defined modern data center, whether it's cloud, private cloud, virtualization, is the fact that you can reprogram things, and you can reprogram them very, very fast. NSX is an entirely API-driven model. I can say I want to change firewall rules immediately. I can change routing, switching rules immediately. I can insert new third-party security services. I can take a virtual machine and say, you have to pass through Palo Alto before you do anything else, right? All these things are programmable, changed, and kind of instantly sort of configurable. So that's the ability to automate security policy can be a very powerful response tool. You don't have to ask people to, reconfigure things in hardware. Again, going back to the RSA case, we literally got to the point during that breach where someone had to go downstairs to our data center and unplug the Secure ID backend system, right? Just take it off the network manually. That was the sort of quote-unquote remediation mechanism that had to be put in place. A lot of that was personnel driven. They were trying to work things through EMC and trying to figure out what was right, what was wrong. But at the end of the day, there was no easy hooks to adjust or configure infrastructure on the fly. Certainly not in the network the way we can do it today with NSX. So this idea of doing automation can actually be a very powerful security response tool and automation tool for incidents. So it's these things together that actually make the virtualization layer a very interesting place to place these controls. And especially when it comes to things that require more embedded understanding and more alignment with your infrastructure, it becomes a extremely powerful mechanism. So I would say, we are not and probably will never be the foremost experts at being the latest and greatest threat research and malware research company out there. What we are really good at is understanding sort of how and where you can place I'll call it access control rules, least privilege rules, where you can start enforcing boundaries and controlling things at the infrastructure layer. Our ability to see these things across these different dimensions makes it a very interesting point to enforce least privilege. And I like this slide from Gartner because it sort of talks to really the fundamental sort of power of the premise in the sense that when you think about trying to protect your data center workloads, and you think about what people normally do, which is install AV at the top end of the pyramid, it's really one of the most least ineffective models out there to actually really secure the environment. If you really want to secure it, it's not the most effective thing. And it's not just us saying this. This came from Gartner. It's in part of their, what they call the Cloud Workload Protection paper. And it's actually a paper that, when they say cloud workload protection, they're talking about really any modern data center endpoint for the most part, whether it's private cloud, public cloud. And if you look at the bottom of the pyramid, they talk about things that they consider core workload protection strategies, the things that are absolutely core, right? And clearly, vulnerability management, the most fundamental thing. I don't know if you've seen any of the recent breaches that have happened. I mean, almost all of them could potentially be mitigated if you properly patched and handled things from a vulnerability perspective. But right above that is network segmentation and firewalling, right? It's a core fundamental strategy that if you create least privilege in the network, you can significantly stop and lower the attack surface. But then if you look at the three rungs right above that, the system integrity monitoring, application control and whitelisting, and exploit prevention, these are things that we looked at and said, look, we're doing network segmentation very well. What can we do in the actual compute stack that can be round out these core workload protection? And that's where AppDefense, the product that we launched a couple weeks ago, comes into play. It sort of helps round out what you can do from a base perspective and sort of build in this more granular application level of control. And what I mean by that is, you know, if you think about a firewall knows what ports and protocols and what information you can use on a channel. So it might say, hey, port 80 is allowed to be used, all good. A lot of things can go through port 80 that might be bad, right? That might be malicious, that might be just things that are abnormal. A lot of applications on the back end could be listening on port 80 and trying to do things that are nefarious based on information that's being sent over that port. A firewall, you know, says port 80 is good or port 80 is bad. That's its understanding and its control point. What we can do with AppDefense is start looking at who's using port 80, how is it being used, what are the type of things that they're doing, and have that extra layer of control such that you won't have anyone manipulating the usage of that known good port or that port that you expect to be used for the application, if that makes sense. One good example, again, just to hit this point again, is at VMworld we did a demo where we showed command injection, remote command injection, which is someone hitting an application server and sending commands via the application server interface, right, which is port 80. And we showed how easy it is to take advantage of a vulnerability in an application server and basically take ownership of the app server itself. We showed it live. We did a complete ownership of the app server. And at some point, just doing some remote command injections, we were sitting there in a console, hitting a Palo Alto data center, having complete control of the application server machine, which is very similar to the recent attack. If you've heard a lot of the things that have been thrown around regarding the use of Apache struts and how that had the vulnerability and all these kind of things, it's essentially the same thing, which is if someone creates an app on top of these web frameworks, and those web frameworks have potential vulnerability points, you more or less have a channel. You've opened up a channel for a good attacker to be able to get it. So based on that command injection attack, what we were able to do is show how looking deeper at the application and the way the application is behaving, we can actually control, manage, and stop that attack right from the beginning, right? Because we know when the application server itself is being manipulated or changing its behavior. And we know that by just having this extra layer of information. So this is the premise of AppDefense. So again, I talked a little bit about NSX. I didn't go into depth on it. I'm happy to answer questions about NSX after the session if you're interested in more detail. But just to give you a little bit deeper dive into AppDefense itself, there really are three capabilities in the product, right? The first is this notion of what we call creating the intended state. So if you really want to start controlling behavior at the application level, you really have to be sure that you know the way the application should behave, right, in the first place. And I talked about how the virtualization layer is an interesting place to do that. But there are things that we do even inside of that flow that make this a more robust system to understand intended state. This is a problem for any system designed around least privilege. You have to understand good behavior in order for you to be able to control it. So we go through this phase of creating what we call a virtual machine manifest. Think about a virtual machine manifest as a set of credentials, right? A birth certificate for every VM, where at any point in time, the hypervisor can say, let me see the credentials that you have, and let me make sure that what you're doing matches those credentials. So every virtual machine in the AppDefense world carries around this manifest and says, this is what I'm supposed to be doing, how I should behave, based on the way I was set up and configured. That second piece of the virtual machine enforcing, or the hypervisor enforcing, inspecting, and managing this behavior is this detection piece in the middle. This is where we actually determine whether there's an anomaly. This is where we enforce and control behavior. And this is where, essentially, think of it this as the security guts of the system, right? Where we're actually building in the control points. We also make heavy use of the hypervisor in this model, which I'll touch on in a second. And then the last piece is this response mechanism. So like, if you think about it, understand intended state, detect when things are potentially moving from intended state. The last piece is, well, what do you want to do if something violates intended state? The simple answer is block it. I just don't want it to run at all, right? Which you can do. The other answer is, well, what if I can do more complex remediation actions? What if I can do things that are a bit more nuanced or a bit more orchestrated? So given the fact that we have access, like I said, to the programmable interfaces of ESX and NSX, we can do things like automatically snapshot the machine. So for forensic analysis later on, you can get access to it. If someone is doing something like manipulating the operating system kernel, trying to change the way the kernel behaves, we can suspend the virtual machine altogether. Again, we showed this live at VMworld last week. It's a great video. I'd recommend you guys watch it, where the attacker tried to shut off AppDefense. They tried to actively kill the AppDefense mechanism. We recognized that. We killed the machine immediately. We just suspended the machine immediately, right? So these are all response mechanisms that can be taken as a result of events that happen. And the other thing that we could do here is hook into the NSX remediation mechanism, which is this notion of NSX having the ability to not only change things that are happening directly on the machine, but change things that are happening in the network and the service chain, the security service chain. So the point here is that you can remediate both on the ESX side and the NSX side together.
Talk about the product and what it does. I'm that guy, but if you want to talk about buying it, sorry, that's what they do.
The city of San Jose has no sales folks here, so.
I'm so glad.
Just getting a live feed from the.
Question?
Yeah, we're getting both sessions at the same time. It's 2-for-1 sale here.
Let's pick up with you again.
Okay.
I think we've figured out if one of these other mics.
All right, no problem. All right, so how do you do this? Like, how do you create this contextual awareness? And just for the interest of time, I'll skip over some of these things. So the first thing we want to do is kind of build into this model of continuous understanding of your application. So this may or may not apply to a lot of people in the room, but clearly what we're seeing now is developers, infrastructure owners, they're moving faster, they want to get quicker, they want to get more agility in the way they do their job. So what we want to do is kind of tap into that, feed into that cycle of when you're building applications, when you're changing infrastructure, when you're deploying them. We want that to be integrated in so that the security people are getting information about changes in the environment proactively and not reactively. And that's not necessarily normal, right? What's normal is typically like infrastructure owners have to go through a security review, a quote-unquote security review. Like when we launched AppDefense, I went through 2 months of security reviews with the VMware internal security team. And that was us with the engineers sitting in front of our security team, explaining to them every single detail about the application, the way it should behave, the way it shouldn't behave. Extremely manual and tedious. Now, the challenge is we push to production every Tuesday. Are they going to meet with us again another 2 months every single time we push to production? We can change behavior anytime we want at this stage. So, and they kind of know this, like it's a kind of well-known kind of game between the two of us. Like they know we can change it at any point in time, and they're kind of like saying, yeah, can you just let us know if you do that, right? But I mean, clearly, we kind of try to use our own discretion as to when we think things are real security-specific changes versus not, because it's a burden to tell them what's happening and what we're changing. So what if we can build this review process into the notion of like integrated into our build and deploy process, right? So this is essentially what we do with AppDefense in this sort of creation phase, right? Just to give you a deeper sense of what's happening here, the first thing that we do is we hook into vCenter and we get an understanding of all your inventory coming from vCenter. And each one of those machines, when it's first pulled in from vCenter, we mark it as what we call an unclassified machine, meaning that we don't know anything about it. It doesn't have any credentials. We don't know why it exists. It's completely unclassified. And the goal is to move as many machines as possible from this unclassified state into what we call protected state, which means that we know their normal behavior and we're watching and controlling that behavior. In order for us to do this, there's this middle zone, which is we call the discovery or creation phase. So the first thing we start to look at is, do you have any configuration management systems that tell us information about those machines? I imagine that, some of you may not. You may use things like CMDBs, content management databases. You may use tools like Puppet or Chef or even VRA, which is a VMware tool to do infrastructure management. All these things are infrastructure config systems. And they're used, for infrastructure admins to do things like control and manage their environment. So we tap into those things. We create a model of intended state based off of what we see from those systems coming in. Again, going back to the demo, we did a really good example showing Puppet, which is a normal infrastructure configuration tool, how we pull in some of that behavior. And just to give you an idea of the examples we can get, we can understand, are you deploying a Tomcat machine for application servers? Are you deploying a database machine? Which database is it? What application does this belong to? Is this part of the mortgage application? Is it part of the HR application? Is it part of the finance application? So we start to get some grouping and understanding of the app in this process. The next thing we do is we hook into application automation systems. So again, may or may not apply to you, but when we deploy our product internally, we use a tool called Jenkins. We have a number of automation systems in place, but we have Jenkins, and then we have the Maven for builds. These systems have a lot of embedded knowledge about the app itself. They know what we're deploying. So with AppDefense, we actually build plugins for these systems where when you deploy something via Jenkins, we can actually understand exactly what are you deploying in that machine and what do you expect to happen. Now, a lot of people don't have these things. So in all cases, what we will do is we will manually learn behavior happening on the machine. So the goal is try to get as much what we call kind of the authoritative information coming from the frameworks that you have built in. If we don't get access to those systems, if you don't have them, you just don't feel like connecting them, you don't feel like configuring them, we will default to learning at runtime and using a machine learning algorithm in the back end to connect that runtime behavior to expected application behavior. And again, just to give you a slight more detail on that, what we can see is if you're using, let's say, port 8080, and you're using port 8080 with this specific process hash, that will correspond to Tomcat, for example, using the machine learning algorithm. We do that in a couple of ways. We use reputation feeds coming from whitelisted vendors like Carbon Black. We have a back-end system that's tracking all of what we call application templates, normal behavior for applications. And then we have a clustering algorithm that kind of connects the two things together. So given that runtime learning, we can start classifying the machine on your behalf. And then all you have to do at that point is just verify that we got it right for the most part. So think of this as, if you have the data stored in a content management database, give it to us. If you don't, we'll learn about it and we'll tell you about the expected behavior. And all of this now becomes the virtual machine manifest, right? The virtual machine manifest gets created and then pushed down to the machine. And once it gets pushed down to the machine, let's skip over this. That's just a view of what the product looks like. Once it gets pushed down to the machine, that's when you can flip on the sort of switch to say, now I want you to start watching and managing and protecting this environment. And when you do that, this is where we use the hypervisor in a very interesting way. We start to, at that point, do a couple things. The first thing the hypervisor does is it says, I'm going to watch over the operating system kernel to make sure no one manipulates or changes or messes with the operating system kernel at runtime. And I'm going to create a protected portion of memory, what we call a protected zone, in the guest operating system, so that you can place this manifest and this control point inside of the guest. And the reason why we place something inside of the guest is we want to be able to, number one, see what the operating system sees exactly. And number two, we want to be able to stop and control behavior before it even gets out of the operating system. And to do that, we have to be inside of the guest. So the hypervisor's job, think of the hypervisor's job as enforcing and controlling integrity of the environment, right? Its job is to make sure that, think of it as a tamper evident seal on top of a bottle, right? So like, if you crack the seal, the hypervisor immediately knows, hey, someone has changed or manipulated or tried to mess with the integrity of the system. And then this is a real-time check. This is not a, we're going to check every once in a while, we'll poll the system every once in a while. Because of the fact that we have this real-time view of any memory manipulation, this is something that happens instantaneously. So this is what we showed in the demo. Someone tried to manipulate what's running in the protected mode. Even if they change a single bit, we get immediate notification and we can take action based off of that. And we do this for the operating system kernel, and we do this for our own AppDefense module that's inside of the guest. And then the AppDefense module in the guest, its responsibility is to take the manifest, observe all behavior happening from the guest, file events, process events, network events, and ensure that those events match what the manifest is. So when you do this, you can actually have a very, very granular level of control, right? Going back to the ransomware example, where you have ransomware that's using known good channels, things that are open because they have to be open, but they're manipulating those channels in a way that are not normal. That's the way they propagate their attacks. We were able to stop WannaCry. We ran tests with WannaCry immediately because we saw it positioned on the machine. It started to use a known good channel. Immediately we were able to say this is not a process that should be using that channel, and we killed it. That's kind of the power of having this well understood intended state model and the power of then watching it in real time at all times with AppDefense. And again, it's an extra layer of defense on top of what you can do with a firewall. I mean, firewalls are good at determining what are good channels, what are bad channels. They're not really good at determining what's using that channel and how it may be manipulating that channel. So then this last piece is this notion of automated response. And again, this ties back into how potentially sophisticated your security operations workflow might be. Again, the first response that you can take in any case is you can just block things. If you aren't comfortable with blocking, you can run things in what we call alerting mode, which you're just getting alerts and saying that when we see anomalous behavior, we'll just tell you about them. The other things that you can do, though, is you can hook back into ESX and NSX to start taking these more complex actions. A good example is like full packet capture. You know, if you want to do full packet capture of network packets in the data center, if you're going to turn that on by default from a regular modern data center, you'd be overrun with data, and you'd probably spend a ton in sort of storage cost for that data to retain it. And then you'd have people just sitting in front of the screen watching over all that data, which 99.99% of it is completely useless information. So what we can do with things like AppDefense is we can say, look, we see an anomaly in behavior. Let's say the machine starts acting abnormally, and we can start full packet capture on demand for that application. We can even do things like start encrypting data on the wire or on the disk based off of anomalies that we see. And all of this is controlled via the ESX and NSX hooks. So just one last piece on architecture, and then we can wrap up. I'm happy to answer questions after the session. So AppDefense is delivered as a cloud managed service. It is a SaaS service that we deploy, unlike NSX, which is an on-premise installation. The reason we did this is, if you know, recently we launched something called VMware Cloud on AWS, which is our ability to run VMware stack software on top of the AWS hardware. We wanted AppDefense to essentially have a position to watch both on-premise environments and cloud environments. So that's essentially what we do. We deploy a small proxy on-premise that communicates with your management systems like vCenter, NSX, and the other VMware management systems. And we obviously communicate with the workloads themselves. But all of that gets fed up to the cloud manager as sort of a user control point, a policy management control point. So that gives us the ability to watch across both cloud and on-prem, number one. But also, more interestingly, it allows us to start using some of the collective data, going back to that machine learning algorithm, to more effectively tell you what's normal, what's not normal. So we can say, hey, this Windows 2012 database, you know, it's acting like 99.9% of the other machines that are out there with the same profile, or we can say that it's acting differently. So that's kind of the deployment model. So again, this is GA'd. We actually launched it at VMworld. I would recommend taking a look at some of the videos. I don't have links in this deck, but I probably should have done that. But you know, we have a great YouTube video where we did a full hour live demo. You know, Tom Korn, who runs security products, gave a pitch on AppDefense, and he's usually pretty good at that kind of thing. So I would certainly recommend taking a look at that if you're interested. We also, Pat Gelsinger, our CEO, launched this on stage with folks from IBM Security. So I'd certainly also look at that if you have time. And then obviously we have a bunch of other assets. So if you just go to vmware.com/appdefense or vmware.com/nsx, you can get all details related to these products. Any quick questions before we have to wrap? I know it's like we're coming right up on time.
What's the performance cost?
Yeah. So the performance cost in the CPU is pretty in line with other things that you'll see with AV. So we run at about normal rate, about 0.5% of CPU utilization to run AppDefense. The reason for that is if you think about a normal model of looking for bad, you have to watch and evaluate every single event and kind of evaluate that against the bad model. We don't necessarily have to do that because we know the exact behavior of the machine. We keep a list of, let's say, 100 approved behaviors. All we do is watch the behavior, see if it matches this list of 100. I mean, think about 100 versus 27 million bad things. It's a lot easier for us to look up that list versus looking at 27 million bad things, right? So it's actually very fast to do that check. The things where we start to see performance impact is when we do have to do memory integrity management. To do that, we have to actually pin down memory pages on the machine, which is why we only place it on the kernel. Otherwise, it would cause a little bit of performance issue. But right now, we're seeing 0.5% CPU utilization on our normal rate. And then for network connections, we're seeing for TCP throughput exactly the same. UDP, we're seeing like a little bit like 10% impact on UDP, but that's, I think, because the UDP is establishing new, there's not a session that's established, so every time it communicates out, we're rechecking that behavior. Okay? Happy to answer questions afterwards. So thank you.